So actually, this is the first time of the in-person class. So I believe the computer systems in this room is not ready for the in-person classes. So I think you can see this slide, but I cannot use the touch screen or work compatibility here. So unfortunately, I cannot write something on this slide deck. Also, oh, it's a hybrid class actually, because it's someone are tested positive, then he or she need to attend the online classes. So I provide the hybrid classes, including in-person class and in-person class and online classes. So sorry for inconvenience. And then actually it looks like this is the first class of this course. And then I hope everyone can hear well, because I'm wearing mask. So it's actually, so this is my first experience to provide the lecture while wearing this mask. So I hope everything is going well. So okay, let's get started. In the previous class, we learned about the power consumption of the computer systems. So this is the equation of the dynamic power. So actually, there are two kinds of power consumption in the computer systems. It's a dynamic power and static power. So dynamic power means that the computer consumes electric power while computer is working. And then what is the static power? Even though the computer is not working, the power is consumed. It's because actually, as the semiconductor technology node is advanced, then we are using the very narrow channel, Cmos channel in our semiconductor devices. So actually, the Cmos transistor is similar to the switch. It's an electrically controlled switch. But the problem is that this channel is not closed completely. That means the transistor is not turned off, even though this device is controlled to be turned off. So that is the source of the static power. But in this course, we do not explore some advanced level of the computer architecture. So I just mentioned the dynamic power consumption. And then, as you know, so this is the equation. If you see this equation, then you need to know which factor influences the dynamic power consumption of the computer system. So power is proportional to capacitive load. So its capacitive load is the overall capacitance in our entire circuit, and then the square of the supply voltage and then the clock frequency. So we can calculate the power consumption of the computer system based on this equation. And then also I mentioned the power consumption by Cmos scaling. So you need to remember that the power density means that the power consumption in the unit area, but actually theoretically, even though actually the size of the transistor is reduced, that means that the technology is advanced, but we can reduce the dynamic power consumption of the single transistor with this Cmos scaling. So, but as the size of the most transistor is reduced, then that means we can include more transistors in the unit area. So actually, the reduced power consumption is a scaling factor is the 1/s², and then the number of transistors in a unit area is s². Okay, so if we multiply both vectors, then it becomes 1. So Dennard scaling means that the power density of a transistor, the power density of a chip is constant. So which means that if the chip size is the same, but if the semiconductor technology is advanced, then we can include more transistors. That means that we can make better CPU or better processors, but power consumption is the same. So without investing more power, then we can improve the performance of a processor. That is Dennard scaling. But okay, the problem is that the Dennard scaling actually ended. So actually, in the unit area, the power consumption is increased. So that's why we cannot use a very powerful single core processor. So actually, this is called the power wall. And then because of the power constraint, we cannot develop the very fast or very powerful single core processor. So as you can see this graph, you can find that the performance of a single core processor is saturated. So it looks like yes. So then what's the solution? What's the possible solution? So we cannot actually, with this advanced semiconductor technology, we cannot improve the performance of a processor. So another possible, then the possible solution is multi-core. So which means multiple core. So core means the independent processor unit. So that means that a single program or single thread can be executed on this single core. So each core, but we cannot increase the performance of a single core. So we added more cores. So actually in the previous class, I covered the latency and throughput. So with this multi-core architecture, we cannot improve the latency. So that means that we cannot reduce the latency of a single thread, but we can increase the throughput. That means amount of work done within unit time. Okay. So in the previous class, I also mentioned the benchmark. So this benchmark is the standard program which measures the performance of a computer system. So we need to use the same program actually to compare the performance of two different computer systems. So that application is called benchmark. And then I mentioned the spec benchmark is the most popular benchmark suite. So we can measure the performance of your system and my system and other systems using these spec benchmarks. Actually, there are many different kinds of benchmark. So for example, if you want to measure the performance of machine learning applications, then you can also use the machine learning benchmark suite like MLPerf. So actually, this spec benchmark is the traditional benchmark suite. So, and then also you can find some many various applications included in this spec benchmark, but you can find only very traditional applications such as compiler, data compression, then some image processing, and so on. So actually, we cannot find any machine learning applications in this spec benchmark. So if you want to measure the performance of different kinds of applications, then you can use other benchmark suite. Then, actually, I already explained. So this table shows how we can calculate the spec ratio. So I mean, it's actually the same. So how can we compare the performance of two different systems. We can just measure the execution time, and then we calculate the ratio of two different execution times. That means two different latencies. It's the same. Spec benchmark also provide the execution time of each application here, and execution time of each application on reference machine. So this is the reference time. And then we can compare the execution time of measured on the some test bed system. That is the system which whose performance is measured. So we can also measure the execution time on our own machine or on the test bed machine. And then we can compare this execution time. And what is this spec ratio? So actually, this value divided by this value. So this is the spec ratio. And then also there are many different kinds of applications in the spec benchmark suite. So, and then as you can see, the performance of these different kinds of applications is also different. So you can find some different spec ratio values. So we can calculate the average based on these multiple spec ratio values. We use the geometric mean. So this is actually this is constrained by the spec benchmark suite. Also, I mentioned, so we can also use the other different kinds of benchmark spec power to measure the power consumption by workload level. So also, in the previous class, I explained about the improportionality in the server systems. So which means that it looks like this. Even though no application is working on this server system, but server system still consume electric power because the power is on this system. So actually, the power is not proportional to the workload level. So even though the workload is 0%, then computer system consumes power. So it's waste of energy actually. So you mean the data center is very large, and then actually data center consumes very much energy, much electric energy. So and then that is a cost. So think like this. So Google provides the very powerful and a very big data center for us. Really, right? We do not pay some money for using Google data center, but you can pay some money for some storage space in the Google data center. But usually, no one pays money for this Google data center. Who pays? Google pays. So the company needs to reduce the electric energy or electric power consumed by its data center. What problem is that the energy, the power consumed by server system is not proportional to the workload level. So if this is proportional, the power consumption is proportional to the workload level, then everyone is happy. So Google is happy actually, the data center owner, but it's not proportional. So this is another research topic in the computer system. Okay, so now I will discuss about the Moore's law. So actually the Moore's law is the very popular law. So who is Moore? Who is this one? Who is Moore? So Moore is the actually Moore is a name of the Gordon Moore. So he was a CEO of Intel Corporation, so CPU manufacturer. So actually, Moore's law is very it's very popular. It's not. It's not. It's important actually in the CPU industry, and then also it's a very popular law. So, but why do we need to mention this Moore's law? The Moore's law is not actually a serious theoretical law. So it's not serious. So what does that mean? The Moore's law means that the Gordon Moore just observed some trend in the microprocessor, and then this CEO, Intel CEO, just to make a empirical law. So it is actually this law is based on the observation. So what is the observation? So what's this? So what is Moore's law? The performance or number of transistors of CPU. Which one is right? So Moore's law means that this is the in-person class, but it's the same to the online class. No one answers. No one answers. Which one is right? The performance of a CPU or the number of transistors in a CPU? Yes, right. Okay. Yes, the Moore's law mentioned the number of transistors in a CPU will double every 2 years. So what does that mean? If we purchase a CPU chip, then in every 2 years, then the number of transistors in this new CPU is double of the previous CPU. The CPU sold 2 years ago. That is the Moore's law. So actually, the Gordon Moore, Intel CEO, just observed some trend, the number of transistors in a chip, and then just made this law. Why is this important actually in this CPU industry? Because it's actually economical law, not the theoretical law. So everyone wants to buy better computer systems. So we invest our money for purchasing better CPU or better computer systems. And then actually this number of transistors determines the performance of our computer systems. And then also I mentioned that the number of transistors. So if we can make smaller transistor, then we can include more transistors in a single unique area, which means that if we scale down the transistor, then we can make the better CPU, better processor. So which means if the semiconductor technology continues advancing, then the Moore's law will also continue, because the CPU manufacturer, like a semiconductor fab, like TSMC or Intel, make their goal, the technology goal, based on the Moore's law. So if you are interested in some CPU industry, then you can find that Intel also announced some roadmap of their CPU, also the roadmap of the technology node, the semiconductor technology node. So you can find that 10 nanometer like 2018 or 5 nanometer, 3 nanometer, blah, blah, blah. So actually this goal is made based on the Moore's law. So this is the definition of the Moore's law in Wikipedia. So actually the Moore, so as you can see in this graph, the CPU chip, the commodity CPU chip actually follow the trend of the Moore's law. So, this is the y-axis means the number of transistors, and then this is the x-axis is the year, it's the time. So we can find that this graph is nearly linear. And then, the y-axis is the log scale, which means the number of transistors increases exponentially. So that's what Moore's law says, because this means that the number of transistors increase exponentially every year actually. So, but this trend is facing end. So everyone says that Moore's law is ending recently, because as you know, the transistor size is very small. So think like this. So currently, the Intel is using 10 nanometer technology, which means the channel width is just 10 nanometer. So it's very, very small. If this size is continuously decreased, then the width of the channel length may be similar to the size of the element. That means that Java element 맞죠? element, like it's very small actually. But so see this trend of the transistor. So actually this orange colored dots represent the number of transistors in a CPU chip. It grows exponentially. So it looks like the Moore's law continues recently, but we expect that this trend will be saturated in the near future. The Moore's law is ending. And then, as I mentioned, the single thread performance, that is the performance of a single core, is saturating, but it's slightly increased because of effort of architectural research. So some new features, some new architectural techniques are included in the new CPU. So the performance is slightly increased, but it's actually in the past the performance increases exponentially, but it is saturating. How about the frequency? As I said, the frequency is already saturated in early 2000. And then power is increasing, but it's still increasing. But you can see from this time, number of cores have increased. It has increased here. So Moore's law continues since the early 2000s, but the computer actually the CPU manufacturer include more cores, so they cannot increase this frequency, clock frequency. They just increase the number of cores. So Moore's law continues. So this graph shows the Moore's law in DRAM. So so this trend is just decreasing. Also, this graph shows the actual transistor density, and then it's a trend by Moore's law, very old version. So that this gap is increasing. So Moore's law is ending. So this slide shows the 8 great ideas in the computer architecture. So actually the computer architect, that means the computer architecture researcher applied some good techniques and then good research ideas to the process architecture or some CPU architectures. But what is the first line? It's a design for Moore's law. So which means that the CPUs, well, processors is advanced based on the Moore's law. So actually, the Intel is a very famous CPU manufacturer. Actually, Intel's goal is following Moore's law. So they mentioned that we follow Moore's law. But recently, they removed this motto. So actually, because the Moore's law is ending, but actually, the CPU manufacturers or processor manufacturers follows the Moore's law, because it's very important, because everyone wants to buy good processor, better processor or better computer system. And then the second line is the abstraction. So with the many abstractions, then we can develop very convenient computer system environment or computer usage environment. So it simplifies also design. We do not need to understand every aspect of computer systems. That means every layer of a computer system. We can just focus on the some single layer or some interfaces between neighbor layers. Then this is very so important. Common case first. So with the computer, we can run general purpose application. So what does that mean? What does general purpose mean? So which means we can run many kinds of applications, a wide range of applications. But so which means actually the applications have different characteristics. So if we want improve the performance of these different types of applications, then we need to add the very different ideas, very different architectural solutions in the CPU architecture. But it's not a good way. We need to make common case first. So what does that mean? Just find the common cases or common characteristics among their wide range of applications, and then just focus on this common case to just focus on making a common case first. And then parallelism is also important. So actually, the multi-core or some CMPs also applies to this parallelism. And then pipelining. So we will learn about the pipelining in this course, and then prediction, memory hierarchy. Actually, in this course, we will focus on the pipelining and memory hierarchy. Okay, and then reliability. So it's some very advanced issue of the computer system. So these are the 8 great ideas in the computer architecture. Then based on these ideas, then we develop the computer systems or computer processors. Okay. This is the end of the chapter 1. And so any questions in the chapter 1? Actually, I will post the first homework assignment, and then the first homework assignment will include the questions in this chapter 1, which means so you will be asked about the some performance. Actually, the most of questions handle performance of the computer systems, and then some terminologies such as the Moore's law, abstraction, blah blah blah. And then also the question will include some power related questions. Okay? So the first homework will be out after this class. Okay? Any questions in the first chapter? So yeah. Yeah. 네, 좋은 질문입니다. It's a good question. So he asked about what is the static power, and then what is the 0% workload level in the static power benchmark. 한글로 대답할까요? 어쨌든 뭐 여기 이제 서버기 때문에 뭐 0% 워크로드라는 거는 분명히 이제 오퍼레이팅 시스템을 한 상태에서 들어가는 거는 맞고요. 그렇기 때문에 뭐 컴퓨터 자체가 그 전기로 이제 돌아가고 뭐 일렉트릭 파워를 소모를 하는 거기 때문에 사실 완전히 지로를 만든다는 거는 뭐 말이 안 되죠. 뭐 그럼에도 불구하고 뭐 컴퓨터 자체가 소비 그냥 턴 온 상태에서 소비하는 그런 스테릭 파워가 상당하고요. 그 다음에 역시나 말했듯이 뭐 여러 가지 뭐 주변 장치라든지 페리퍼럴즈, 그 다음에 뭐 오퍼레이팅 시스템이 그냥 올라가서 돌고 있는 뭐 그 정도 이제 고려를 하면은 그런 워크로드가 0%에도 그냥 파워가 소비된다는 거는 뭐 말은 되는 거죠. 근데 스테릭 파워가 진짜 이제 좀 문제가 되는 건데 옛날에는 스테릭 파워가 그렇게 문제가 되지 않았어요. 그래서 CMOS 그 트랜지스터 사이즈가 컸을 때는 그 스테릭 파워는 거의 이제 지로에 가깝고 거의 이제 이그노를 할 수 있다라고 이야기를 했는데 점점 이제 트랜지스터 사이즈가 작아지면서 지금은 스테릭 파워가 거의 40%, 50% 정도 차지를 하고 있습니다. 전체 파워 컨섬션 중에. 그럼 CPU가 소비하는 파워 중에서 그 정도를 차지를 하고 있어요. 이거는 무시를 할 만한 게 아니죠. 네, 그래서 그 부분도 지금 계속 문제가 되고 있고요. 네, 뭐 그렇게 이해를 하면 될 것 같습니다. So I said that the static power now occupies about 40% of the 40 to 50% of the entire power consumption by CPU. So this is the critical issue in the CPU, the current CPU design. Okay. So let's move on to next chapter. Yes. Okay. So okay. So actually, as I mentioned in the first class, the chapter 2 of this course will cover instruction set architecture. So actually, the title of the chapter 2 is instructions, language of the computer. So actually, when we mention the language of a computer, then we can think like this. So like C or Python, it's like the programming language. Because we can make applications or some programs using these high-level languages, high-level programming languages. So everyone says that you need to understand the syntax or structure of the programming language in order to write the program code, because computer can only understand the programs written in programming languages. And that's right, actually. But actually, the program language is the kind of software. And then, as I mentioned, computer hardware cannot understand high-level languages, because the high-level languages are very similar to our normal languages, such as English, but computers cannot understand. So then, what does that mean? Instructions, language of the computer. So actually, in chapter 2, we will learn about instructions of computer systems. And then these instructions mean assembly language, not high-level languages like C or Python. So actually, as I mentioned in the chapter 1, the high-level languages are compiled into assembly language first, and then this assembly instructions are one-to-one mapped to the machine languages. That means machine instructions. So actually, the machine code or machine instructions are composed of digital signals like 1 or 0. So we will learn about these assembly languages of the RISC-V ISA, and then its assembly instructions are one-to-one map the instructions which can be understood by computer processors. Okay. So let's see this figure. So actually, this you can find that this figure in some advanced computer architecture book. Like it's a computer architecture textbook covered in the advanced computer architecture course. Okay, so this figure shows the hardware, and then in the above this hardware person, there is a wide plane of the instruction set, and then above this instruction set plane, software person, software people are playing, and the hardware is supports the instruction set and some software people. So what does that mean actually? Instruction set. So what is the instruction set? So instruction set is the set of instruction. That means the group of instruction. And what does an instruction mean? The instruction means it's just the command or instructions. So, but this instruction is defined, and then the computer hardware is designed to execute these instructions. Instructions defined by instruction set architecture. Then, how does instruction set architecture define the result of the computer hardware? So if I think like I cannot watch today. Okay, so think like this: add x1, x2, x3. So that is the example of an instruction. Right? No, I cannot use my finger. So add x1, x2, x3. So actually, the instruction set architecture defines the result of this instruction, add x1, x2, x3, which is x1 equal x2 plus x3. Then what do x1, x2, x3 mean in this instruction? Yeah, right, registers. So our data used by this instruction, add instruction, is a kind of instruction. This data is already stored in the register files, and then instruction with data from two register files, x2 and x3, and then calculate the x2 plus x3, and then store the result to the x1 register. That is the definition of the instruction defined in instruction set architecture. So instruction set architecture define how instruction is executed in the processor. So that's why. So hardware designer, design a computer processor based on the instruction set architecture. That means that hardware needs to generate the result defined in the instruction set architecture. So the hardware designer need to make the hardware system or computer processor based on the instruction set architecture content. So, and then software So I said that software engineers or software programmers do not understand about how hardware works. So they just use the high-level languages, or they just use some software or some. So, but this software, the software written in high-level language should be translated into the instructions. Even so, think like this hardware engineers or hardware also do not. Hardware person also do not. I can use high-level languages, but normally the computer hardware does not understand how software works. So that means that high-level languages about actually hardware does not know about how high-level language works. Hardware just understand the instructions defined in instruction set architecture. Software just understand the high-level language, but these high-level languages are translating the instructions. So instruction set is the interfaces between software and hardware. Okay. So then it's my question. So what is a processor and then what is a computer? So actually this figure shows the concept of a processor or a CPU. So what does that mean? So I said that the processor receives the instructions and then processor generates the result. The result defined by instruction set architecture. But in this figure, you can find that the result is the change of state. So what does that mean actually? So what are result generated by this processor? Actually, the result generated by this computer processor is change of state. What? So actually you need to understand this concept. So instruction means some instructions that performs the arithmetic logic operations. Like arithmetic operation means that add, multiply, divide, like something like that. And then logic operation is the AND or exclusive or some logical operations. So, and then data transfer instructions. So actually all data is stored in the main memory, and then data should be transferred to the registers. So it's the data transfer instruction, and then control instructions. You know, high-level language code, we frequently use if, then, as. That is called the conditional statement. So this conditional statement is implemented using control instructions. So instructions have some different kinds of instructions. So instructions architecture include different kinds of instructions, and then these instructions are given to the processor, and then processor generate result. But I said that the result of the processor is the change of state. And what is changing? Architectural states are changing. Then what are architectural states? Register files and main memory. So which means data stored in register files and data stored in main memory. So instruction set architecture just define this result, change of state in register files and main memory. So we will learn about some different components in computer processors, but you can find many other components many other components, but instruction set architecture just defines the result data in register files and main memory. So, which means the computer architecture researchers can include many different components, such as cache, such as TLB, then some other useful components. But they can make, which means that they can make any other components if these components are good for the performance of the computer processors. Then they can include any components inside of a processor. So that is the some architectural techniques or some architectural ideas in a processor. But instruction set architecture just defines the instruction and this output. So if the computer works, then if this outputs are correct, then it's okay. Okay, so actually some intermediate states. Intermediate states can be different because we can add some more components or some ideas in this processor. But if these final results are correct, then it's okay. Okay. So just to remember this concept of the computer system. The instruction is given to a processor, and the processor generates a change of state. And then change of state is the result of this instruction. And then change of state just include register files and then data in main memory. These two components. Okay. And what is the instruction set architecture? We frequently call instruction set architecture as ISA. This is the abbreviation form of the instruction set architecture, ISA. And then this instruction set architecture just defines the CPU. So actually, if a certain CPU is designed for supporting a certain ISA, then the CPU can just run the applications that includes this specific instruction set architecture. So for example, Intel CPUs can run only x86 ISA, not ARM ISA, because the ARM ISA defines the different instructions and then different result by this ARM ISA. If the CPU is designed for x86 ISA, then that means the CPUs can run the binary code, which is compiled using x86 compiler. So that means actually we can run Linux operating system on ARM computer. Like, recently the Apple computer, Apple uses the ARM CPU, ARM-based CPU. So then it means we can generate the binary file on the ARM-based MacBook or Mac computer. And this binary code, even though the source code is the same, the compiled binary code, this binary code compiled on Mac computer does not run on the Intel-based CPU because instructions are different. So instruction define this CPU and then CPU family. Right? Okay. So and then this is important. Instruction set architecture is the contract, it's a promise or protocol between software and hardware. The hardware is designed based on the contract by instruction set architecture. Also, software generate the binary code based on this instruction set architecture. Okay, so that is the interface between software and hardware. And sometimes we can be confused with the CPU architecture, like microarchitecture. So instruction set architecture is different from microarchitecture. So you know, the Intel also has the various family of the CPU architecture, such as the Haswell, Ice Lake, recently Elder Lake, and then some blah blah blah. So that is the actually that mentioned the microarchitecture. But instruction set architecture of the Intel supported by Intel CPU is the x86. So Intel makes the various kinds of CPU such as the Xeon or Celeron. So actually Xeon can run the binary code compiled using x86 ISA. Also, Celeron can run the same binary, which means the Celeron or Xeon supports the same instruction set architecture. But the microarchitecture of Xeon and Celeron is different, which means the Xeon is the most very powerful, but Celeron is not powerful. So that means the architecture, which means the microarchitecture inside of Xeon and Celeron is different. So you need to distinguish instruction set architecture and then CPU architecture. Okay. So what's the instruction set? So that is the set of instructions. It's a repertoire of instructions in a computer. Okay. So it's like this. So you can list the arithmetic operations like add, sub, multiply, divide. It's same to the instruction set. There are different instructions that support the different operations such as the add, sub, multiply, divide. So instruction set just collects these different instructions that support the different operations. It's just a list, just some group set of instructions. So, and then also I explained this, different computers may have different instruction sets like ARM or x86. And then early computers support the very simple instruction set. But recently, instruction set architecture includes more new instructions. So actually, when the x86 ISA was firstly developed, this x86 ISA just includes about less than 100 instructions. But recently, the x86 includes more than 1,000 instructions because new instructions are included in this x86 instruction set architecture. But x86 instruction set architecture also need to support the old instructions. Even though these old instructions are very inefficient in the modern computer processor architecture, the modern computer processor architecture cannot abandon these old instructions because this is the contract. If the software is, once the software is compiled using x86 ISA, then the future processors, the new processors that support x86 ISA needs to run this old binary file. It is called backward compatibility. So Intel or AMD also needs to support the backward compatibility of this binary file or instruction set architecture. So even though the x86 architecture is very inefficient, so it has very complex and then it includes many instructions, the x86 That means Intel or AMD need to support these inefficient instructions. So modern computers need to support the many instructions. Okay. But we will learn RISC-V instruction set architecture. So see, actually the RISC-V instruction set architecture is it's a somewhat modern instruction set architecture. So it was developed, actually invented recently. So I believe it's about 10 years ago. So it's a very new instruction set architecture. And then this RISC-V ISAR was developed at UC Berkeley. Actually, the author of this book, Patterson and Hennessy, invented this RISC-V instruction set architecture. And then the main feature of this RISC-V is this is the open ISA. So what does that mean? So think about the ARM ISAR. So actually ARM is also very simple and then very efficient instructions. But in order to use ARM ISAR, the companies, some manufacturers need to pay royalty to ARM. So that means they need to pay money to ARM. And then this royalty, maybe it's about 5% or something like that. So actually it's not free. Not to use ARM ISAR, then the processor manufacturer or hardware vendors need to pay royalty to ARM. But the RISC-V is the open ISA. So it's free. It's a free like Linux operating system. So Linux is called the open source operating system. So it's free. It's the same to the RISC-V. RISC-V is also free. And then anyone, so any companies or any students, any researchers can use RISC-V ISAR. And then as the RISC-V ISAR was recently invented or developed, it's very simple and very efficient. But what is the issue of the x86 ISAR? It's very old, and the x86 ISAR has long history. But in order to support the backward compatibility, x86 includes the very inefficient instructions. And the Intel cannot abandon these inefficient instructions. So x86 actually is very complex, and then it has a very large number of instructions. But as the RISC-V was recently invented, RISC-V includes the small number of instructions, and it's very simple. So if you are interested, then you can visit this link. Via this link, you can find the slides and then videos that introduce the RISC-V ISAR. So this slide is just to compare the complexity of the x86, ARM, and RISC-V, and then it's very complex. And the x86 is called the CISC type ISAR. So what is CISC? CISC means complex instruction set computer. So actually, the CISC, this C already includes complex. So which means, oh, this ISAR is very complex. It's not free also. And then it includes the more than 1,000 instructions. And then how about the instruction length? So you mean the assembly code is just a normal word. So it's very similar to the English word, but actually these assembly instructions are translated into the digital signals, digital data. Like, you mean, the digital data is composed of 1 and 0 will be. So what is the instruction length? Which means the size of a single instruction Then that means that this instruction is represented using bits, which means the digital signal. So you can find that the instruction length is various. So it means that the length is 1 to 15 bytes. How about the RMISA? So it's simple. It's simpler than x86 because ARM is called RISC, the RISC, which means reduced instruction set computer. So C means complex and R means reduced. So RMISA is relatively simple compared to the x86 ISA. It's not free. So as I mentioned, the hardware vendors need to pay royalty to ARM to use the RMISA. And then it includes about 400 instructions. So just compare the number of instructions between ARM and x86. You can find that, oh, it's simple. And RISC-V is recently developed, and then it's simpler than RMISA. And then we can use this RISC-V ISA for research, education, and a commercial purpose. Okay, this is a picture of the RISC-V. But I mean, so as you can see, the RISC-V includes the RISC. So it's the same. So which means RISC-V ISA is also RISC type ISA. So which means it's a reduced instruction set computer. And then there are some features about the RISC type ISA. So it's simpler than CISC. So instruction length is relatively fixed. So that means the instructions have same length. Is relatively. So some instructions have shorter length, but usually instructions have the same length for the RISC type ISA. Also, as I mentioned in this slide, RISC type ISA supports the data transfer instructions. So actually, the data transfer instruction means that the data transfer instructions supports the operation of the data transfer between register file and main memory. Actually, other instructions such as the arithmetic, logical instructions cannot use data in main memory because this type of instructions of the RISC type ISA just support the operations using data in register file, not memory. Actually, data transfer instructions just handles the data in main memory. So actually, you mean this is data transfer. So it supports the data transfer between register file and main memory. Actually, only this type of instruction can touch the main memory. This is also the feature of RISC type ISA. And then actually the RISC-V supports the different type of ISA formats. So actually IV32E, IV32I, IV64I, and IV128I. So actually this I after this number 32, 64, and 128 represent the integer type instructions. So I means integer. So which means integer means 정수 in Korean. So just support the integer type instructions. And then 32, 64, 128 represent the width of a single general purpose register. So which means the size of the data handled by these instructions. So if we just mention the RV64I, so which means that this RV64I ISA supports the integer instructions, and then the size of the register file, that means that the width of the register file is 64. So which means this RV64I can handle 64-bit data. Okay, so the number represents the width of the register file. And then RV32E is the 16 registers. So we actually the RISC-V define that means that requires 32 register file. So we will learn about the register file later. So that is the number of register files. So but 32E is has only supports the 16 register files. Okay, and then this integer type ISA just include the 50 hardware instructions. So actually, with this simple integer type ISA, we can run programs. We can make a processor. Okay. And then also we can add the more instructions supported by extensions of the RISC-V ISA, and then we can if M is included after this I, then which means that it's the M type extension of the RISC-V, which means the M type instruction includes the multiply and divide instructions, and the A means atomic type instructions, and then F means the single precision floating point. So we will learn about the single precision later. D means double. And then G means general purpose ISA, which includes the IMAFD. And then Q means the quad precision. So based on these extensions, then more instructions can be included. Okay. But in this course, we will learn RV64I. Okay. What does that mean? In this course, we will cover RISC-V 64, which means the width of the register file is 64-bit. So which means it's a 64-bit computer. And then we will just cover the I-type instructions, which means integer instructions. And also you can compare some size of the instruction and complexity like this. So actually this slide shows that RISC-V is very simple and efficient. So, and then this is the reference card of the RISC-V, and then I will post the reference card and then instruction set manual of RISC-V. So you can read this reference card, and then also you can read the instruction set architecture manual of RISC-V. And then if you see this reference card, then you can find this is a category of the instruction, like the shift instructions and the arithmetic instruction is here, and logical, branchy, and jump and ring, any other instructions. Also, if you see this column, the rightmost column, so you can find the assembly instruction of the RISC-V here, and then the format of the instruction. So, for example, add RD, RS1, RS2. So add is the instruction. So which means that this instruction performs add operation. The RD represents the destination register. So which means that the result of the add is stored in the RD. RS1 represents the source register 1. RS2, source register 2. So the data in source registers are read, and then the two data is added, and then the result is stored in RD. Okay. So if you can understand, if you can read this reference card, you can find some formats like here, and then so definition of the instruction. So if we just see this some representation, then we can understand how we can estimate, not exactly understand, but we can estimate how instructions will work. Okay. Actually, you can instructions have the similar format. If you see the exclusive OR performs the exclusive OR operation, RD, RSO, then we can estimate the operation of the XOR. And then other OR same, the similar, sub, blah, blah, blah. Okay. Okay. So I briefly covered the brief instruction of the RISC-V ISR. So I just explained some meaning of instructions in architecture in the today's class. So I'll stop here, and then so it looks like this is the first class again, and then but some devices are not ready for the in-person classes. So sorry about this inconvenience. And then, but I'm very happy to see your face in the classroom. So actually, this is my first in-person class in Korea University, because when I employed in the Korea University, and then the COVID-19 was 2020, and then the COVID-19 was starting. So I just provide the online classes. But now I can see the students' face. Then it's good. Okay, thank you for attention, and then see you in the next class. And then remember that the first homework will be posted on the Blackboard and then Piazza. Okay, thank you.